So, welcome back student. So, in the last class we stopped with a very important concept by saying that two functions phi I x and phi j x, suppose these two functions, if the inner product of these two functions is 0 with I not equal to j, then these two functions, we say that these two functions are orthogonal to each other. Okay, before going to further this orthogonal thing in detail, let me do one thing once again, that which is related to linearly independent and dependent functions. So, say these functions we have a set of functions. Now, we know what is the meaning of inner product of a function. So, that is why it is a correct place where I can put another thing to find out another recipe rather to find out whether the functions are linearly dependent or independent. Now, these things normally people, I mean there is a process we know, but it is this process is a little bit trickier than the previous process, the Wronskian process, but still I believe it is important that you should know that this way also you can find out whether the functions are linearly dependent or independent. So, let me do that, you will readily understand what is the meaning of that. So, I have C1 phi 1 x plus C2 phi 2 x plus Cn phi n x is equal to 0, that is my equation. So, what I am doing here, I am again try to find out whether the set of this function is linearly dependent or independent, but not using the Wronskian method that we discussed in the previous class. Rather, we are doing something different, because now we know what is the meaning of inner product. So, now what I will do, that I will make another equation by taking the inner product of both the side with phi 1. So, if I do that, then I will have something like this, then something like this. I am making the inner product of both the side. When I make inner product of both the side, as if I am doing this operation both the side, phi 1 I am operating over this. So, when I am making C1 and this quantity is nothing but this inner product notation in function space. Then finally, I have Cn phi 1 phi n is equal to 0, right. I have one equation, this is my equation 1. I also have equation 2 with C1. Now, you can readily understand that in the first line, if I make a inner product with phi 1, then in the next line I will do that for phi 2. So, it will be phi 2 phi 1 plus C2 phi 2 phi 2 this, and go on. I will go on up to my n equation. My nth equation will be C1 phi n phi 1 plus C2 phi n phi 2 plus Cn phi n phi n. So, now I have n equation in my hand. It is the same way we use the thing we use in forming the Wronskian. Here we will have the same thing. So, these are nothing but the numbers, these are the number. For non-trivial solution, I will just have this. For non-trivial solution, I I will have this matrix in my hand. So, I need to find out this quantity. So, this matrix, whatever the matrix form I have, if I make the determinant not equal to 0, then I can readily say that there is a this function, whatever the function I have, is linearly dependent or not dependent. It depends on whether it is 0 or not, exactly the same way that we have in the previous case. But the determinant in the previous case was the function and their derivatives, but here the inner product of the functions. So, in this case extra you need to do that, you need to find out the inner product of the entire thing, but it is not that cumbersome in the no, if you note that this quantity phi 1 and phi 2 and phi 2 and phi 1 is not different, because if they are real quantity, because these quantity are the same quantity, and this particular determinant is normally defined by G. This is called the Gramian. This is called the Gramian, like the Wronskian, this is called the Gramian, and this method is called the Gramian method. So, this is called the Gramian determinant. This is nothing but the Gramian determinant. So, I can have my function, I can make a inner product, series inner product of these things, and then I find the derivative, then I find the determinant of these things. When I find the determinant is equal to 0 or not equal to 0, readily I understand we have a non-trivial solution or the trivial solution, and this things is called the Gramian method. You can use also the Gramian method to check whether I can have the linearly dependent or independent solution. If it is not equal to 0, obviously it is linearly independent. If it is 0, then there is some kind of linear dependency over that. I wanted to say, because in many places, in many books it is not there, but this is another way to find out. This is Wronskian is not a only way to figure out whether a function is linearly dependent or not. This is another way to find out whether the function is really linearly dependent or independent. But the only thing is that in Wronskian you do not need the concept of the inner product, but here you have you need to have the concept of the inner product. So, that is why I show that after learning the inner product, what is the inner product we have. So, that is the thing. Now, go back to our original problem, which was the inner product problem. So, let me have some function 1 x square. Now, try to find out whether these functions are orthogonal to each other or not. These are linearly independent functions that we proved in the last class. So, now my goal is to find out whether they are orthogonal or not. They are orthogonal or not. I should put a question marks here, not that marks. Okay, they are orthogonal. The question is, a set of function is given to me, I want to find out whether they are orthogonal or not. But before that also I mentioned one important thing, that they belong to the continuous function with some limit. Here I need to put the limit, definite limit, because I need to do the integration here. So, say minus 1 to 1. So, first I need to check these two functions, say this is my phi 1, this is my phi 2, and this is my phi 3. So, phi 1, phi 2, I check whether it is 0 or not. If it is 0, then these two are orthogonal to each other. If other things are 0, then all of them are orthogonal to each other. Individually we need to figure out whether they are orthogonal or not. So, this quantity is nothing but integration minus 1 to 1, phi 1 is a function here 1 multiplied by phi 2, which is x dx, this quantity. Now, this quantity is nothing but x square by 2 minus 1 by 1, but before that you can already find that this is a odd function with minus 1 to 1. So, obviously it will be 0. If we do, we will be having a result 0. So, that means phi 1 and phi 2, here phi 1 is 1 and x, they are orthogonal to each other with at least with this whatever the limit I have. The definition of the function is within this closed limit, closed interval. What about phi 2, phi 3? Minus 1 to 1, phi 2 is my x, phi 3 is my x square dx. If I do, then what I am getting here, again x s cube is here. So, it is odd function x to the power 4 by 4 minus 1 to 1, again I have 0. So, this is a odd function with limit minus 1 to 1. So, I should have value 0 here. What about phi 3 and phi 1? These things, then I need to do the integration with 1 multiplied by x square dx. Now, here you can see one important thing, that this two quantity here, if I multiply, so we have a even function in our hand. So, it will be x s cube divided by 3 minus 1 to 1, which I suppose is 2 by 3, but not equal to 0. That means, even though these functions are orthogonal, these and these are orthogonal, these and these are orthogonal, but these and these are not orthogonal. So, according to the definition, it is not that these and these are orthogonal and these and these are orthogonal, then this has to be orthogonal to these two. It is not necessarily. In vector maybe that is possible, but in function theory it is not the case. So, with this kind of treatment, you can find out a set of given set of functions are orthogonal to each other or not. Okay, let me find out another set of function. So, say 1 cos x, cos 2x, cos nx and so on. I can extend this function up to infinity. I can extend this set of function up to infinity. I can anyway I can do up to 3, but in general I can extend these functions. So, now I need to find out whether, so this is my phi 1, this is my phi 2, if I note in terms of phi, this is my phi n and so on. So, first I need to find out whether any general component, if I take say phi 1 and general component phi m, this quantity. By the way, these functions belong to the continuous functions with minus pi to pi limit. So, now I have this. So, again I need to check individually whether they are orthogonal to each other or not, but here what I am doing, since this function is cos, I take the general function and then check for any value of m or n these functions are orthogonal or not. So, first my definition minus pi to pi, and then phi 1 is 1, I have cos m x dx. This is the function I have. What is the value of this? Cos m x the integration is sin mx divided by m with minus pi to pi. Now, we know that sine of m pi is always 0, where m is an integer. Here 1, 2, 3, 4, 5, 6, all these things are integer. So, if I put this here, so if I put m as integer, then this quantity is nothing but 0. So, that means phi 1 and phi m are orthogonal to each other. Whatever the m you take, it will always remain orthogonal. So, I will invariably I can take any functions that will be orthogonal to each other. Now, the other things, because this is 1, so that is why I need to do in this way. Now, I need to do a general thing, phi m, phi n, phi m, this, where m and n not equal to 1, this is something defined value. So, my integration will be something like that, cos of mx multiplied by cos of nx and these things. Now, we know how to do this integration. If I take half here minus pi to pi here, then 2 cos these things can be splitted to cos m plus n x plus cos m minus n x. Like this. Now, it is easier for us to integrate this quantity. If I integrate, will be sine of m plus n over m plus n, and that quantity will be again sine of m minus n minus n with minus pi to pi with the limit this. When you make the limit here like this, again the same thing, the sine of m plus n, which is again an integer multiplied by pi. So, this quantity will going to vanish and this quantity will going to vanish. So, overall I will have a 0. So, that means I have a set of functions cos x, cos 2x and all these things. When I make the inner product of the entire functions, I find that any m or m value, they are 0, they are always 0. So, that means this is really a set of orthogonal functions. So, this is indeed a set of orthogonal functions. This is a set of orthogonal functions. With this note, I can give you another homework. Since this is done, so please check, I am giving another set of functions like this. Please check whether this is a set of orthogonal functions or not. I check that this is a set of orthogonal function, but this is a homework for you people who are taking these courses. Please sit down and do the same calculation and find out whether they are orthogonal set of function or not. Again, they are in same close interval, they are continuous in same close interval. So, that is valid here also. Well, now I know this set of functions are orthogonal to each other, but one thing is important, that whether they are normalized or not, that is important, whether they are normalized or not. That means, if I take this quantity, whether it is 1 or not. So, in order to check that, again I need to do the same thing, but now I will take any phi m to phi m. So, when m is 1, that means I will do the integration, this is for m is 1, that is 1 into 1 minus pi to pi dx. I am making the inner product for the same function. So that I can find out the norm of this function. So, if I do, then I will find it is 2 pi. This is x, x is pi to minus pi, then it will be 2 pi. This 2 pi is basically the value of phi 1 square. So, what is the norm? What is the norm of the first function? Is root over of 2 pi. Root over of 2 pi is the norm of this function. Well, I should note it here somewhere, that my phi 1 was root over of 2 pi. Next, I will do for other cases. So, I will do the same quantity, I will do the same calculation, but for here m is not equal to 1, greater than 1. So, that means when I greater than 1 means I will take now the cos and all these things. So, that means it is minus pi 2 pi cos square m x dx, any m, whatever the m you can consider, this is the case. Now, I can do in this way, I can take half and make it 2 of cos square m x, and 2 of cos square m x I can write it as 1 minus 1 plus rather cos of 2 m x. Dx. The first case I will have half, the integration will be simply x. In the second case, the integration will be sine of 2 m x divided by 2 m with the limit upper limit and lower limit minus pi to pi. If I do that, then I will have half, x will be simply 2 of pi, but this quantity when I put the limit will going to vanish. So, finally, I will have something equal to pi, this quantity invariably for all the values of m. So, that means the norm of other quantity is root over of pi. Once we have the norm, then I can readily say that my normalization factor is in my hand. So, what I will do, that I will just change this function. So, initially if you remember, this function was orthogonal, but not normal. Because if I take the norm of these things, I will find this value is not equal to 1. Now, what I will do that, because the norm now I find, I can change this set of function like this. My first function instead of 1, I put 1 by root over of 2 pi. Instead of cos, I put cos of root over of pi. and then cos 2 pi and so on. Finally, we have cos nx root over of pi and so on. So, I modified this function by putting some constant term, and when I put this constant term, now this set of function became orthonormal. That means it is orthogonal to each other, that is point 1. Second point is it is also normalized. So, that means this function can behave like a basis, which is very, very important. So, now they are potential bases, they are potential bases. So, in the vector space, if you remember, there the concept of the basis is coming in exactly in the same way. And what is the meaning of the basis? The basis of meaning of the basis in the vector space was, if I have a set of function in which I call basis, which can expand or through which I can write any vector, then these functions, whatever the vectors we have, called the basis. So, that means any vector can be represented in terms of the basis. In the similar way, in the function space, I can potentially write any function in terms of the basis functions. So, let me generalize this before concluding this class. So, that means I have a set of functions phi I x, phi 2 x, phi n x, like this, say finite set of function for the time being. This is an very important thing, because this should not be finite, this should be infinite, but let us consider I am taking a finite set. These functions are orthonormal. When I am saying these functions are orthonormal, that essentially means phi m phi n is equal to delta m n. This things is the inner product notation. So, inner product of any function with m and n is delta m n. Next, I am saying any function f x potentially represented as C 1 phi 1 x plus C 2 phi 2 x plus C n phi n x, this form, or in more compact way C I phi I x I running from 1 to n. Please remember that this equal sign I should not put here like this way, because I am taking only the finite set of functions. Here the dimension of this function is dimension of the function space is infinity. If the dimension of function is infinity, potentially I should have infinite number of basis functions. So, this function if I able to write here, so basis function also go to infinity. If I say I will like to write this function up to n number of functions, basis functions, then this f x will never be equal to the right hand side, whatever. So, this is a very important thing you should remember. In principle, f b tends to equal to will be equal to this when n tends to this n tends to infinity. That means I will try to find out what is my f x by taking 3 or 4 terms. Obviously, the right hand side will never be represent the original function. Now, I gradually increasing my number of functions or number of bases. If I do that, then I will gradually go to the original function whatever the function I have. So, that is the gradual process. If I go to more and taking more and more and more and more function, I will go more and more and more and more towards the original function, that is f x. So, there is a error, obviously there is a error associated with that. So, this is a very interesting problem and it is related to the Fourier series. So, in the next class gradually we start from here, that how a function can be represented in terms of the basis functions, and the number of bases, if I take the limited number of bases, the functions which is represented by the basis functions shouldn't be same, but if I take that to up to infinity, then we will find that these things gradually give you the original functions. So, that is nothing but the Fourier series, the well known Fourier series, that you know that any function can be represented in terms of the basis function. Here the basis function, whatever the basis function we will take is nothing but the sine and cos, but you can take the different kind of basis function also, and in that case you will get the different polynomials. Some polynomials are there which can also be a potential basis function. We will also going to learn that. So, with this note, let us conclude that in the next class. So, today's class, very important thing we find that what is the basis of the function, what is the meaning of basis of a function, and next thing is that how a function can be expanded in terms of basis, and this is basically the building block of the Fourier series that we will cover in the next class. So, with that, so see you in the next class. Thank you.